Good day and welcome, students and viewers. In this video, we are going to look at relations. We're going to look at binary relations, types of relation, and so on. Relations. This is our topic for today. The course code is MATH101. The title of the course is Sets and Number Systems. In our last video, we have looked at what is the Cartesian product. If you have a set A, you have another set B, then the Cartesian product of the two sets, A and B, is A cross B. That is the Cartesian product. And that is giving you an ordered pair, A, B, where A is coming from the set A, and then B is coming from the set B. So this is what we have as the Cartesian product. And if you have a set, for example, equals to 1, 2, 3, and you have another set, B equals to, say, A, B, then the Cartesian product of A and B, which is written as this, is a set containing the ordered pair 1A, so we have 1A. Remember, the first element is coming from the first set, while the second element is coming from the second set. So we have 1, B, and then we have 2, A, and then we have 2, B, then we have 3, A, we have 3, B. So this is it. This is the set A cross B. So it's a set of all ordered pairs A, B. Where A is coming from A and B is coming from the set B. So can we find B cross A? Yes, we can find B cross A. This is the set of all ordered pair where the first element is coming from B and the second element is coming from A. So we have A, 1, and we have A, 2, A, 3, and we have B, 1, we have B, 2, and then we have B, 3. So this is the set of all ordered pairs A, B, where A is coming from B and B is coming from A. It is clear that A cross B is not equal to B cross A, unless the set A is the same thing as the set B. So if you have A cross A, then it's commute. So A cross B, if you have two distinct sets, A and B, then A cross B is not equal to B cross A. What about the size? The size of A cross B, this is equal to the size of B cross A, even if A and B are two different sets. Look at this. We have 1, 2, 3, 4, 5, 6 elements. So we have 1, 2, 3, 4, 5, 6 elements. So the size of A cross B is equal to the size of B cross A. And that is equal to the size of A times the size of B. So once A and B are finite sets, then this is always true for the two sets and for the Cartesian product of the two sets. Thank you. In today's video, we are going to focus our attention to a kind of notion called relation. In fact, we are going to be dealing with binary relations because we are dealing with two sets. So here, a relation, so let's start with definition. A relation are from a set A to another set, say B, is a subset. It's a subset of the Cartesian product. Of the Cartesian product A cross B. So a subset of A cross B is called a relation. And so sometimes we use R to relate two elements. So now, if A is an element of a set A, and B is coming from B, it's an element of B, then the relation of A and B is written as A is related to B, or that A comma B is in A. So this is a relation from A to B. The relation is originally from the set A to the set B. So we write it as A comma B as an ordered pair belonging to R, not A, sorry. So belonging to R, where R is the relation. So if A and B are related under the defined relation, then we write A comma B belong to R. So we write A comma B not in R. That is, A is not related to B. When A is not related to B, we can take example. The first example here in this video, the first example in this lecture is to define a relation, you have to know the set. So if you have your A is equal to A, B, C, and D, now a relation on A given by, so you have R is equal to, a relation is a set of ordered pairs. So you have A, comma A, you have A, B, you have A, C, and you have B, C. Or you have C, B. So let's take this as a relation. So from this relation, we clearly write, because A is related to A, so we say A is related to A. But we also write B, A is related to B. But B is not related to A in this relation. A is related to B, but you can see B is not related to A anywhere. We can also see that B is related to C, and C is also related to B under this relation. And so one can quickly simply write this as A, B, comma A is not in R, meaning it's not a member of R. And so B is not related to A under this relation. So we now give example 2. Example 2. Let A be equals to the set containing 1, 2, and 3. Let B be equals to a set containing 3, 4, and 5. So, and let this R be defined as, say, 1, 2, 2, 3, and then 3, 4, 4, 1. So you see, this relation, 1 is related to 2, but nowhere 2 is related to 1. 2 is related to 3, 3 is not related to 1. So you see, you write 1 is not related to, we write 2 is not related to 1. And 3 is not related to 2. Because it's an ordered pair. Just because 2 is related to 3, you cannot say directly that 3 is related to 2. 3 is related to 4, but 4 is not related to 3. This is very obvious and clear. So now let's look at the inverse of a relation. Inverse of a relation. So definition. Let R be a relation. On a set. On any set, say A. The inverse of R, written as R inverse, is the set R inverse equal to B comma A, such that A comma B is in R. So that is the inverse of a relation. Take for example this relation here. The relation is given. So how will you write a R inverse? So R inverse is equal to, from this example, from example 2. The inverse relation of example 2 is 2, 1. See? In R, it is A, B. In R inverse, then you reverse the order. That is all. Just reversing the order of a relation makes the inverse of the relation. And that is how to obtain the inverse of a relation. So you have 3, 2. Here you have 4, 3. And then you have 1, 4. This is the inverse of this relation. Now an exercise. Write the inverse of the relations on the set A equals to 1, 2, 3. So R, number 1, R is equals to 1, 2, 2, 3, and then 3, 1. 2. So R2 is equals to 3, 1, 3, 2, 3, 3, and then 1, 1. R3, this relation is given by 3, 3, 1, 1, and then 2, 2, and then 2, 2. Write their inverses. Is R equals to R inverse always? If yes, fine. If no, under what condition? Under what condition is R equals to R inverse? So now, because we have understood what a relation is, so let's talk about composition of relations. Composition of relations. How do we compose relation? Let R and S be two binary relations on any set. The composition of R and S, written as R composition S, so a small circle between them to denote the composition of relations. And so it is the set of all relations R composition S, which is equals to say A comma B, such that you have A comma X is inside R, A is related to X in R, and X is related to B inside S. So this is it. So is the relation set of all relations AB such that A is related to X in R and X is related to B in S. Can we give example? An example here is, so this is example number 4, I think. Yeah, this is example number 4. So let R be equals to, say, 1, 1, 2, 3, and then 3, 4, and then 1, 2, 1, 3. This is R. And S be equals to the set of all relations 1, 2, 2, 3, okay, so we have 3, 4. What is R composition S? So R composition S is the set of all ordered pairs. The 1 is related to 1, and 1 is related to 2 here. 1 is related to 1 in the first set. 1 is related to 2 in the second set. So we write 1 related to 1 here, and 1 is related to 2. So 1 is related to 2 directly. 2 related to 3. 3 is related to 4. So we have 2 related to 4. So we write 2 is related to 4. And we have 3 related to 4. So 4 is related to nothing here. 4 is not related to anything, and so the relation 3 related to 4 does not have a pair in this composition, and so it is lost. So 1 is related to 2, 2 is related to 3. So we have 1 is related to 3. 1 is related to 3, 3 is related to 4 here. So we have 1 is related to 4. So this is, so we start with types of relation. Types of binary relations. One, we have the reflexive relation. Reflexive relation. By definition, we mean a relation R on a set, on any set, is called reflexive. It's called reflexive if for all A in set, say call it A. For all A in A, you have A is related to A. That is, A is related to A. For all A, every element is related to itself. That is, you have A comma A in R. For all A in A, all the elements of the set under which the relation is defined, over which the relation is defined, the element is self-related, is related to itself. So, this is reflexive relation. For example, the relation of being a subset, this subset is a reflexive relation. Reflexive relation on a collection of sets. You have a collection of sets, you have a universe of sets. Every set can be compared with any other set. If you pick a set, say set A, you can compare it with set B, you can compare it with set C in terms of containment. And in fact, every set is a subset of itself. We have seen before that for all A in the universal set, you have A is related to, A is a subset of A. For every set, this is always true. And so, the relation of being subset is a reflexive relation because it compares between a set and itself. So, every set contains itself as a subset. So, this is a reflexive relation. This is example 6. Example 7. We have the relation of this. Now, this relation of less than or equal to is a reflexive relation. It's a reflexive relation on the set of, say, real numbers. Pick the set of numbers, then this is reflexive because every number is either less than or equal to itself. So pick a number, say A, then that number is either less than or equal to itself because of the equality, and so the relation is reflexive. Likewise, the relation of being equal to is a reflexive relation on the set of numbers. Any number, any set of numbers, be it a set of rational numbers, set of real numbers, set of natural numbers. So the relation of being equal to is a reflexive relation. And the relation of being less than or equal to is also a reflexive relation. Example 8. Consider this relation. Consider the relation R equals to 1, 1, 2, 2, and then 1, 2 is a reflexive relation. This is a reflexive relation on the set. Call it A equals to 1, 2. This is a reflexive relation. Why a reflexive relation? Because every number is related to itself in the relation. Don't bother about other relations. What you need to check, only a reflexive relation, is the set is 1 and 2. The set is containing just 1 and 2. So, check, is 1 related to itself? Yes. Check the next number, 2. Is 2 related to itself? If yes, then the relation R is a reflexive relation. Alright, if one number failed to be related to itself, then the set, the relation there is not a reflexive one. For example, this is example 9. This relation R equal to 1, 1, 2, 2, and then 3, 3, and then 4, 1. On the set A equal to 1, 2, 3, 4. This relation is not reflexive. Why not reflexive? Because 4 is not related to 4 in the relation. And so it is not reflexive. Even though 1 is related to 1, 2 is related to 2, 3 is related to 3, but 4 is not related to 4. And so the relation R on this set A is not a reflexive relation. Now we look at the symmetric and anti-symmetric relation. Symmetric and anti-symmetric relation. Symmetric relations. Definition: a relation R on a set A, a relation can be defined on a set or can be defined from a set to another set. So on a set, A is called or is said to be symmetric if, for all A, B in R, B, A is also in R. So this kind of relation is referred to as the symmetric relation. If the inverse of the relation is always in the relation, then we call this a symmetric relation. So in other words, you say a relation is said to be a symmetric relation if you have R inverse is contained in R. If the inverse of the relation is contained in the relation, then you call that relation a symmetric relation. Can we give example? Example 10. Consider the relation R is equal to, say, 1, 2, and then 2, 3, and then 3, 2, 2, 1, and then 1, 3. On a set A equals to 1, 2, 3. So we want to check, is this relation R a symmetric relation? So R will be symmetric if 1, 2, for all 1, 2, there is 2, 1. For all the relations AB, BA is in R. So 1, 2, do we have the reverse or the inverse? So do we have 2, 1? Yes, we have 2, 1. 2, 3, do we have 3, 2? We have 3, 2. So 3, 2, there is 2, 3. 2, 1, there is 1, 2. 1, 3, there is 3, 1. We have 3, 1? No. So consider the relation is not symmetric on A. It's not symmetric because 1, 3, there is no 3, 1. And so the relation is not symmetric. So another example, the relation of being parallel on the set of straight lines. Is a symmetric one. Is a symmetric relation. It's a symmetric relation. Why? Because if you have line AB, a line segment AB, if it's parallel to the line, let's say CD, this would imply that the line CD is also parallel to the line AB. If you have two parallel lines, those two pair of lines are parallel. They are pairwise parallel. I mean, they are parallel to each other. If AB is parallel to CD, likewise CD is also parallel to AB. And so the relation is symmetric. The relation of being parallel to on the set of all straight lines is a symmetric relation. Let's look at anti-symmetric relation. Antisymmetric relation. Definition? A relation R on a set, say A, is said to be antisymmetric if for all relations, A comma B inside the relation R on the set A, if you have A is related to B and B is related to A, so I mean B is related to A under the relation, this implies A and B are equal. It means A is equal to B. Meaning two items are related and inversely also related, then the two items are the same. For example, so this is example 11 here, so we have example 12. You see, the relation of being a subset of, I mean this relation on the collection of sets is an antisymmetric relation. How? Since if you have A is a subset of B for any two sets, A and B from the collection of sets. So if you have A is equals to B, the A is contained in B and B is contained in A, this implies that what? A is equal to B. It's an anti-symmetric kind of relation. So A is related to B and B is related to A, definitely A is equal to B. So this is an anti-symmetric relation on the set of all, I mean on a collection of sets. You consider any two sets and they are somehow related by being a subset of, one is a subset of the other and the other is a subset of the first set, then the two sets are equal. We look at the last kind of relation. So we have the transitive relation. Transitive relation. So a relation, a definition, say a relation R on a set, say A, is called transitive if you have A is related to B and B is related to C, then A is related to C is also in R. Yeah. If you have A is related to B and B is related to C, then A is related to C under the same relation. Whether you put in R or you do not put in it, we understand what we mean. So example number 13. So the relation, this one, on a collection of sets, of subsets, or sets, is a transitive relation. Yeah, it's a transitive relation. Since we know that if you have A is a subset of B and B is also a subset of C, it is clear that definitely A is directly a subset of C. And therefore the relation of being subset is a transitive relation. Another example 14. Let R be equals to A comma B and then B comma C and then A comma C. And then we have AB, we have BA, we have AA. On the sets of A, B, and C. Is this relation R a symmetric relation? Sorry, is it a transitive relation on R, on the set this of ABC? To answer that, we have AB and we have BC. So we should have AC in the relation. We have AC? Yes, AC is here. So we have BC. Do we have CD? We don't have CD. Good. AC. Do you have C something? No, we don't have. Okay. We have AB. Do we have B something? Yes, we have BE. So there should be AA in the relation, and AA is in the relation. And so this relation R is a transitive relation on the set of A, B, and C. It's a transitive relation because whenever A, B is inside, we're going to look at, here we have studied the types of relations. We have defined relation in the beginning of our video. We have seen the types of relation, namely the reflexive relation, the symmetric relation, the anti-symmetric relation, and the transitive relation. In our next video, we are going to look at equivalence relation, and then we are going to look at equivalence relation with partition. Thank you very much.